Hello guys and welcome back to my channel Civil Construction and Tutor, and in this video I'll show you how to compute wind load for pitched roof. So basically we'll be using this Excel sheet which is based on IS 875-2015, and we'll compute the wind load as a pressure, that is area load. And we have two options: either we can go for the area load or we can just divide those loads and apply it on the purlins. So we'll see that later on. So starting this Excel sheet, we'll require certain basic dimensions of the building which we can take from the model or even we can take from the architectural drawing. So for now we are calculating the wind load for this building particularly. So now going back to the case, so these are the dimensions that we require. So width of the building, length of the building, lower height of the building, so that will be up to the point from where the truss starts, and rise of the truss will simply be this region. Rise of the truss, lower height of the building, and this as the width of the building, and then we'll get the alpha, that will be the roof angle. Now let us see in our case, and make sure that W is from this point to this point. Do not include the projections. So width of the building 12.9 meter, length of the building you can take that from the x direction, so it will be 0. At this point it is 44.4. Lower height of the building, so lower height of building will be considering from the ground level. So this is below the ground level, so that will be the ground level 0, but it is 3.71, so we'll subtract that value. So till that point it is 15.86, so 15.86 minus 3.71, that will be the lower height of the building, 12.15. And for the rise of the truss, so this will be the central post, we'll consider this height, so this is basically 2.5 meter. So roof angle 21.19 degree, so that is okay. So the pitch of this roof is kept slightly higher considering the snow load, so 21.19 degree. Mean life of period. So now coming back to this formula, K1, K2, K3 into VB. So we'll get the regional speed for that location, and that has to be multiplied by parameters K1, K2, K3, which is basically design probability factor, terrain roughness factor, topographic factor, and importance factor. So for computing the probability factor, we require mean probable design life of structure and design wind speed. So considering our case, the design, obviously the structure is very important, so the mean life period will be 100 years, important buildings, and basic wind speed for our case is 47 meter per second. You can check that from the map as well. The class of the building depends upon the dimension of the structure. So if the dimension in either case is greater than or less than, then we will be considering a certain case. For example, if it is less than 20, it will be class A. If it is greater than 50 meter, then it will be class C, and if the dimension is between 20 to 50, then it will be class B. For that we have to consider the terrain category as well. So we have definition of category 1, category 2, category 3, and category 4. So this is a powerhouse structure that will be built at a open terrain area, and it might have certain obstructions between 1.5 to 10 meter. And make sure that the trees are not considered as an obstruction, because there is no guarantee that the structure or the tree will be there for its throughout its lifetime. So it is better not to consider the tree as the obstruction. So for now let us see category 2. The life period is 100, okay, that makes sense, and wind speed is 47. So the value of K1 will be 1.07. Similarly for the other value, that is K2, which is simply terrain category factor, the building of the height is 12.15 meter and terrain category is 2, coefficient that is the class B, then the value should range between 10 and 15 meter, that gives 0.98 and 1.02. So we get the value of K2 as 0.997. That is interpolation between these two values. So I have got a table over here and we get the interpolation. So K3. Now K3 is simply the effect of topography will be significant at a site when the upwind slope theta is greater than 3 degree, and below that the value of K3 may be taken as 1, and even if it is greater than 3 degree the value will range from 1 to 1.36 degree. So for now keeping this as 1. Now K4 is simply importance factor for the cyclonic regions, and you can get that from this table, that is from the clause 6.3.4, which says on the basis of the structures we have to consider the value of K, and even if it is in the cyclone regions only. If it is not in the cyclone region we don't have to consider, that will simply be 1. For now it will be 1. Now we get the value of Vz, that is design wind speed, which is 50.15 meter per second. Now we'll compute the design wind pressure 0.6 Vz square. Now we get this value as 1509 Newton per meter square. Now design wind pressure, we get Pz times Kd into Ka into Kc. These are other parameters that has to be multiplied with. So Kd is simply wind directionality factor, Ka is area averaging factor, and Kc is the combination factor. Now if we see this from the table, Ka area averaging factor, that depends upon the tributary area. Wind directionality factor, that depends upon the direction of the wind, and Kc being the combination factor. So we'll consider all those things. So the value of Kd you can take as 0.9 or 1, and for the cyclone affected region also the value of Kd shall be taken as 1. We'll take this value as 0.9. Now Ka area averaging factor, so that depends upon the tributary area. So what actually tributary area is? Now let's see here. So we have a tributary area for the roof this much over here. So considering the width and the spacing of the truss, 12.15 by 9, that gives us 109.35, which is greater than 100 meters square. So we can use this area averaging factor 0.8. Similarly Kc, which is basically combination factor, we can get that from 7.3.3.13, and I have got this table. So if you see here, the combination factor depends upon the design case, and for our case that is basically pressures from windward and leeward walls in combination with positive or negative roof pressures. So we can get the value as 0.8. So we get the value of design wind pressure as 869 Newton per meter square, and minimum design wind pressure. So we have to compare the design wind pressure with one of the minimum value that we get from the clause 7.2, and that says the minimum wind pressure should be 0.7 times of Pz, and that comes as 1056 Newton per meter square. So we'll be considering the minimum wind pressure, and the design wind pressure finally it will be 1056 Newton per meter square. Calculation of design load, that will be live load and dead load. So for the live load up to slope 10 degree, in case of accessibility not provided, the live load is 0.75 kilonewton per meter square, and as we have slope of 21.19 degree, we have to increase or decrease on basis of the slope we have. So for every increase in the slope, there will be decrease in the live load, so it comes as 0.53. Spacing of the purlins, so as I said we have two options. Either we can apply load directly on the roof truss, sorry, the seating element over here, the CGI sheet, or we can just apply load on the purlins. So it is better to apply on the purlins because it will be a one-way loading, or you can just model the roof truss and apply the load as a uniformly distributed frame load for the area. So for now the spacing of the purlins, let us see, it is 1.075. so here we have spacing of purlin 1.075. So live load per meter will be 0.57 kilonewton per meter. If it was a area load, it would have been 0.53 kilonewton per meter square. Now we are distributing that load in the purlins. So multiplying with the spacing of the purlins, we get the value as 0.57 kilonewton per meter. Similarly, weight of the roof covering. So general standard corrugated GI sheet, we have roofing load as 0.10 kilonewton per meter square. Spacing of the purlin is 1.08 meter. So we get the roofing load as 0.11 kilonewton per meter that will be applied on the purlins. Then we have wind pressure as per IS 875. So which says F is equal to CPE plus minus CPI into A into PD. So CPE and CPI are the coefficient, that is internal and external coefficient, and that depends basically the internal pressure coefficient depends upon the openings. So if we see from the clause as well, so internal air pressure in a building depends upon the degree of permeability of cladding to the flow of air. So in case of less than 5%, the value will range from 0.2 minus 0.2, and for value 5 to 20%, the coefficient will be 0.5 and minus 0.5, and if it is greater than 20%, the internal pressure coefficient shall be taken as plus minus 0.75. So in our case, the opening will be less than 5%. So that makes more critical with the external pressure coefficient. And we have to compute now the coefficient of that is the external pressure coefficient, and we can use this table 5, that is external pressure coefficient for pitched roof of rectangular clad buildings, and it depends upon the building height ratio and the angle of the roof. And we have wind angle theta is equal to 0, wind angle theta is equal to 90 degrees. So if we see that in the plan, so basically this will be the theta, considering this as the wind. If it is theta is equal to 0, that is perpendicular to the ridge, and the other case will be theta is equal to 90 degree, that means the angle of the wind from this direction, that will be parallel to ridge. And we have phase EF and GH. So if the wind is coming from this direction, the windward side will be EF and the leeward side will be this one. And in case the wind is coming as theta is equal to 90 degree, EG will be the windward and FH will be the leeward if the wind is coming from this direction. Now going back to this side, so I have made a table like this. So H by W less than 0.2. So we have this parameters EF, GH, something like this. So for 1 by 2 and 3 by 2 and 3 by 2 by 6. So for now H by W, so 12.15 divided by the width height is 12.15 and width of the building is 12.9. So that gives us the H by W ratio as 0.94. Slope is 21.19 degree. Hence, coming that falls in this case 0.5 and 1.5 and 20 to 30. So 0.7 minus 0.2 minus 0.5 minus 0.5 minus 0.8 minus 0.8 and minus 0.6 and minus 0.8. So we get this value interpolated for 21.19 degree. So we get the value for EF, GH and EG and FH. Now CPE we have, CPI we have, we'll substitute the value in this way because we have PD, and A will be considering per meter square, so it will be simply be as 1. So we get the value minus 465 minus 888 minus 316 and minus 739. So all of them are negative, that means a suction effect. So at the roof we'll have a suction effect, and on the other side as well we have this case, whichever the value, all the value here are upward, that is negative, that means uplift force. In some cases we might have downward pressure as well. For example, if the slope of the roof increases, value of net pressure coefficient becomes positive for a higher pitch. If we have a higher pitch, then we'll have a downward force because that will make the resultant of the wind load dominant in the downward side, and that could be more critical. Now we'll consider the maximum load of this. So basically these are in Newton per meter square, and if we divide this by 1000, that will simply give us the value in kilonewton per meter square. So here the maximum is, irrespective of the sign, the maximum absolute value is 1.056. So that is 1.06 kilonewton per meter square, and considering the spacing of the purlins, we get this as 1.14 kilonewton meter. Now we can apply this load on the roof. So I will show you both the ways. You can decide whichever you want to go with. So define now. Here firstly we'll draw an area. So basically if we are using ETABS, then we don't have the option of assigning the area load as uniform to frame. So in that case we just have the option of uniform to cell. So we might have to go for the uniform load as the frame load if we want to directly apply on the purlins. So for now let me show you the way. So we'll apply this as a wind load, coordinate system as local. You can simply turn on the local axis, Control W, and you get the option of local axis for the areas. So R is the local axis 1, G is the green, that will be 2, and 3, that is blue. So RGB, local axis 3, and we have option of one way or two way. So considering this as one way, and live load per meter, apply. So we need to see whether it is applied as our case or as we have decided. So we can simply go to display. Here you have display, show object load assign. Go to the area and simply select wind. Make sure this as one way. So it has been applied in this direction, which is not our case. So what we have to do is simply go to assign, and here we have area, local axis 90°, apply, and now select here apply. Now we get the value, right? But one thing we have done here wrong is the loading. So that should have been in the upward direction, because it is being resolved, it has been resolved into two directions. So we are not getting the exact value that we wanted. So the next thing we can do is simply select the purlins, right, and then go to assign frame load, distributed, and wind load. Make sure the local axis, and for frame we generally apply in the direction 2. For area it was 3, for frame it is local axis 2. See the green one, local axis 2. Now the frame load is 1.14. So in the direction 2, so it will be positive, that makes sense. Okay, apply. Apply. So now let us turn up the local axis. It is being a little bit confusing. So if you see here, we have the wind load in upward direction, that was the local axis 2, but there is certain inclination of the roof, so the purlins has to be inclined, or should be in certain inclination, that local axis. So for that we can simply go to frame, assign, here we have local axis, and we'll rotate that by the angle we have. So it was 21 degrees, maybe negative in this direction, so apply. Now simply select any one of these and we'll check whether it is true or not. So display, frame, wind load, frame local, apply. See, the load has been applied in this direction, and if we go with the current display system, we'll have two values, that is one for the horizontal and the other for the vertical. It has been resolved. So that is the case with the frame area load as well. And in this direction it will be positive 21 degrees, don't get confused. So it was negative 21, it will be positive 21 for this side. And for the purlin at the outer edge, it will be half of the load that is being in this purlin, because it shares load from this half area and the half of this area. But for the purlin at the edge, it will simply take the half of the load from this CGI sheet. So if it is 1.14, then obviously for this it should be half of the load that we have considered, in this way, right? So also resolve this, that is the angle for the local axis of this frame. So in this way the load for the pitched roof is computed and applied on the model. I hope this video helped you, and if it did help, do like and comment in the video and subscribe our channel, share with your friends. Thank you.